1.8 is about a new theorem called the Squeeze Theorem. This theorem is sometimes also called the sandwich theorem or the pinching theorem. So this is what the sandwich theorem or squeeze theorem says. If f of x is between g and h of x, so g of x is less than or equal to f of x, which is less than or equal to h, and the limit as x goes to c of g and h are the same thing, then the limit of f as x goes to c will also be the same thing. So the purpose of the squeeze or sandwich or pinching theorem is that f is a big, ugly, messy function. So f is this ugly one. It's the bread in the sandwich. Sorry, it's not the bread. It's the meat in the sandwich or the peanut butter if you're a vegetarian. So f is stuck between two pieces of bread, but it's a mess. Okay, it's pinched between two other functions, but it itself is difficult to evaluate. However, the two functions are not difficult, and they both have the same limit as x goes to c. And since they have the same limit, our function also has to have that same limit. So that's how the squeeze theorem works. I'll do an example to see if it helps make a little more sense of this. All right, so the first thing we need to do is make up a useful g and h. We are the mathematicians, we have to come up with g and h. If our g and h are not useful, it either means that we didn't do a good job of making them up, or this isn't a good candidate for the squeeze theorem. The way we are going to choose g and h is we're going to, and these will almost always, and certainly always if it's specific, involve a sine or cosine function. First thing we do is we plug in 0. We get 0 squared times sine of 1 over 0. But 1 over 0 is infinity, and sine of infinity doesn't make any sense. The input for that sine function is terrible because it's sine of infinity. But I know, because I know the sine function, that I don't care what the input is. No matter what the input is, the sine function is always going to be stuck between negative 1 and 1 because the sine function has a range from negative 1 to 1. It can't get any smaller than negative 1 or any bigger than 1. So as I'm making up a useful g and h, I'm going to make use of that fact, and I'm going to say, well, let's let g of x be x squared, which is this part, x squared, times, instead of this big ugly sine function, times negative 1. Now, I know for sure that x squared times sine of 1 over x can't be any smaller than this, because sine of 1 over x can't be any smaller than negative 1. Do the same idea for the other piece of bread. I'm going to say, well, I'm going to let h of x is going to be x squared, and then instead of sine of 1 over x, I'm going to say 1. I know for sure that x squared times sine of 1 over x can't be any bigger than x squared times 1 because sine of 1 over x can't be any bigger than 1. Now I'm going to do the two limits. So I'm going to find the limit of g and h. So I'll take the limit, and this limit is going to be as x goes to 0 because that's the limit I care about. So I'm going to do the limit as x goes to 0 of x squared times negative 1. And I think you'll agree that this limit is pretty easy. I can just plug in 0 and I get 0. Now I'm going to do the same thing for h. So I'm going to find that limit. And again, this limit is easy to find. It's also 0. And they match. They're the same number. So that means that that is also the limit for my function. So from all of that sandwich theorem work, I can conclude that the limit as x goes to 0 of x squared times sine of 1 over x, which I don't want to evaluate because I don't know sine of infinity, that limit also has to be 0 because it's pinched between two functions that have a limit of 0. Here's our second example. I partly put this example in here so that you wouldn't always think the answer is 0. It's not always 0, but it often is for these problems. So I don't want you to think it's always 0. I'm going to encourage you to pause and try this on your own and then come back after you've tried it. But I'll walk through it now. So the cosine function is the part in here that has a restricted range. The cosine function is always going to be, I don't care what the input is always going to be between -1 and 1. I am going to 0. I have a limit as x goes to 0, so I have cosine of infinity, which doesn't make sense, but that's okay because I know that the output won't be any smaller than -1 and it won't be any bigger than 1. So one of my functions is going to be 2 plus x times -1 over 3. And the other function is going to be 2 plus x times +1 over 3. I know that the function that is ugly and messy will never go outside of that range because the range of cosine is stuck. Now I'm going to look at each of those two functions individually. So I'm going to do the limit as x goes to 0, because that's the limit I care about, of 2 plus x times -1 over 3. And that limit, if I just substitute 0 in for x, is 2/3. And the limit of the other function is also 2/3. And since those two limits match, that means that I can conclude that the limit of the ugly function that I don't want to evaluate also has to be 2/3. The last example is a limit as x goes to infinity. This process still works even if you're not going to a number, but if you're going to infinity. But sine of infinity is confusing, so we can't directly evaluate this limit because sine of infinity doesn't make sense. But I know that sine itself has to be stuck between -1 and 1. So I'm going to use that fact to make up my pieces of bread in my sandwich. So I know that this function that I'm looking at is always going to be between -1 over x and +1 over x, because it can't get any bigger than that or any smaller than -1 over x. And now I'm going to do each of these two limits as x goes to infinity. Plug in a really giant number, I get -1 divided by a really giant number, I get 0. Same thing on the other side. I'm going to do the limit as x goes to infinity of 1 over x. 1 divided by a really giant number, that also gets close to 0. And therefore, I know that the limit as x goes to infinity of sine x over x is also 0. Because these two limits match. My function is stuck between those two functions, and so its limit also has to be 0. Those 3 dots, by the way, mean therefore in math proofs. This isn't a very careful math proof, but it's kind of a nice way to use our math lingo. That's it for the sandwich theorem, the squeeze theorem, pinching theorem, all the same thing, just 3 different names for it. Good luck.